So thanks a lot. So who's used nanoparticles today?
Probably we have, right?
Right. So who brushed their teeth today? All right. So if you brushed your teeth, there's titanium dioxide and there's nanoscale titanium dioxide, in that toothpaste that you use. What do you do with your toothpaste after you used it once?
Spit it out.
Spit it out. Where'd it go? Right. So there's lots of nanomaterials kind of already, going down the drain. And so I'll talk a little bit about, what these. What is that nice little button? Nanomaterials, kind of walk through these three little pieces. I know I sat through party yesterday. It was really cool to kind of think about, where pretreatment is in here. And we've worked with a number of industries and thinking about, how they go about getting permits related to their discharges in wastewater. So first, what is nano? So it depends in the United States or in Europe. So Europe has a really refined definition of nano. And so you actually have to count all the particles, in a sample and figure out how many are less than 100 nanometers in one dimension. So it was really industry that came up with that definition. And if greater than 50% are less than 100 nanometers, it's considered nano. In the United States, there is a very different, kind of context of nano because it's not regulated really. The only nanomaterial that falls under a lot of regulation is nanosilver because it falls under FIFRA because people put nanosilver. Anyone use Tom's of Maine toothpaste?
What is it?
Tom's of Maine, right? It's a natural toothpaste. So who uses sunscreen? Okay, so which, do you know if you use kind of, oxybenzone and chemical sunblock or titanium dioxide or zinc? Right, so there's two different ones. And one's marketed as minerals, like if you go to a health food store, it's gonna have more of the titanium dioxide and nano zinc. So they're nano because they're transparent. So when you put it on, your skin doesn't get as white. And it actually turns out that they're marketed more towards children because they're viewed as healthier than putting chemicals on. And so this is another oddity of sorts because in Europe, they're banning nano titanium dioxide. In Hawaii and Australia to protect the reefs, they're banning the chemical version of oxybenzone. So, these things that we use a lot of every day are present in nano, and they're there because they have unique properties. So they'll block UV light, and that protects cancer. So they're also used in lots of different products, and I'll talk about them as we go through. So on the far right-hand side are these engineered nanoparticles. You can buy tennis rackets made with carbon nanotubes and different things, right? But in the beginning, in the manufacturing process, at some point they're kind of nanoscale. And that, there's lots of other nanomaterials out there kind of in the environment already that fall in the size domain. And so they're kind of nothing new, but they're kind of engineered to have specific properties, whether it's size, shape, optical properties. I have a daughter, and when she was 15, she took these pills for like 2 weeks so she didn't get acne for the rest of her life. They're like cured acne. But now that you can go online and they massage gold nanoparticles on your skin and they ultrasound it, and you'll do the same thing. You'll never have acne. So there's these alternatives between chemicals and nanoparticles that are out there that people are doing really interesting things in all different fields. And so the amount of nanomaterials, that is engineered nanoparticles, are pretty small still compared to all these other sources of nanomaterials. And so it's really hard. It's kind of like a needle in a haystack finding nanomaterials out there. But this is one of my favorite kind of graphs that a group in San Diego or Santa Barbara put together. So the bigger the color, so the flux of engineered silica dioxide, for example, is the largest nanomaterial class that's used. And you can see titanium dioxide there in blue as well. That's what's in your toothpaste, in sunscreen. It might be in your yogurt. It's in a lot of different foods. It's in chewing gums and different things. Silica dioxide is used in a lot of places, from tires through different food products and things. And you can see that it all flows through kind of that one box there called a wastewater treatment plant. And so how it gets from that source to the wastewater treatment plant is, kind of through commerce and industry in different ways. So you can kind of find your favorite product, and we've done lots of these things. We've looked at a lot of consumer products all the way across the life cycle, from manufacturing facilities into customer care products. Anyone take this Nanosilver? So these are drinks that's supposed to change the ecology of your gut. Has anyone gone into a bathroom, seen these cloth, hand dryers to dry your hands? So a lot of those will have Nanosilver in it to prevent bacteria from growing on it. So as you wash these, say take them back and wash them and recharge them, they'll have a large amount of silver. So after the photographic industry kind of decreased, the amount of silver going into wastewater decreased, and it's actually been increasing again, but now it's through this use of Nanosilver. So it's not coming from photography facilities, but it's going to be coming more from, fabric washing types of facilities. So we can go out there and we can find nanomaterials, and people give us samples and they say, are there nano? So analytically, there's lots of challenges. But in the end, you need to take pretty pictures sometimes to count how many particles are there. So it's difficult, it's expensive, but there are ways to figure out, are there nanomaterials? And you can kind of read through, your favorite foods. These are in Australia. Australia said they didn't use nanoparticles until someone asked us to check. And the only thing is I say, it's not on there. There's, maybe it got cut off there on the bottom, but there's something called chicken salt. So chicken salt has 15 weight% silica dioxide. So why would you put silica dioxide nanoparticles in, a flavor package like, chicken salt, whatever that is? Why would you put that in there?
To prevent it from
Caking?
It's an anti-caking agent, right? The reason they put titanium dioxide in things like yogurt is it gives texture. So if you take these nanoparticles and massage them on your finger, it feels just like really smooth oil, right? So things like a lot of the artificial drinks like orange juice and stuff to give it texture, they'll put in nanomaterials as well. Chocolate has the same texture additives. So texture, anti-caking. So, but is that better than putting fat, right? I mean, so Dunkin' Donuts, coated their donuts with titanium dioxide. So they've stopped that because of pushback. But what do they use now? Right now they use fat. So they use little fattened globulars instead. So there's choices that people kind of make. And some of the, one way we kind of bin these choices is shown in this graph. I've been talking about some of the ones down in the lower left, things like silica dioxide in food. So silica dioxide is pretty inert. It's free, that is, it's kind of in the food or in these food processing or in your toothpaste. And so it's kind of low, it's passive, not very reactive. So the ones that are more reactive are used in other industries. So they're used in industrial manufacturing, but never end up in a consumer product. And a really good example there are polishing agents. So whether it's jewelry stores or this example with cerium oxide is computer chip manufacturers. So they use lots of nanoparticles. They're actually one of the largest users of nanoparticles in the world. So polishing agents will have oftentimes use nanomaterials. And then I talked about things that are kind of embedded onto things or attached to things, whether it's the bottom right, things like carbon nanotubes in a tennis racket, or if you have a lot of the floor coatings, the polyethylene floor coatings, they also put nanoparticles in there to increase the durability of the polymer coatings. Things like nanosilver are attached to fabrics to prevent your socks from stinking. You can put clothes with nanosilver. Patagonia sells these things with nano copper, so you can sweat but you don't grow bacteria, right? It prevents your clothes from smelling. So they can be released during things like cleaning processes. So I just want to spend a time thinking about these chemical, mechanical planarization. This is industrial processing. We worked with the Semiconductor Research Corporation, Intel, HP, and others, trying to understand whether on-site pretreatment is necessary before these are disposed. So in California, for example, the regulations are around copper discharges, And they wanted to understand, did they have to worry about nanoparticle discharges, or what regulation would cover it? And so they thought it would get covered kind of under suspended solids types of materials. So we actually went out and sampled what came out of there, kind of solid separation. So for the most part, it didn't remove a lot of these nanoparticles. In the chemical planarization industry, and when you make these computer chips, these particles are put into water, but they have additives on the surface, so to make them stable in water, right? So they don't stick together. So the same thing that they were adding to make it stable in water really prevented it from being removed during their pretreatment processes. So nanoparticles do get into source systems. And that's kind of the purpose of this. There's all different ways that this can happen, and lots of different sources that are already going in, and it's likely to just kind of increase over time. So I'll talk about another example kind of later with a paint manufacturer that puts carbon nanotubes into paint. The idea there is that the polymer in the paint, by putting carbon nanotubes in, holds that together and prevents it from cracking, like mini rebar inside the paint. But I want to talk a little bit about what happens when nanomaterials get to a wastewater treatment plant. And so there's a wastewater treatment plant, right? And so we've done a number of sampling at these kind of different points through here to understand what's the fate, and ultimately, does it end up in the biosolids, or does it end up in the liquid effluent? So one of the things about almost all these carbon nanoparticles is they don't biodegrade, they don't turn into CO2, that they do go different places. Some of them will dissolve, so things like nano zinc, nanosilver do dissolve, but they also can form in a wastewater treatment plant. So if I have silver ions coming in, it actually can react with sulfide and precipitate nanoparticles. So sometimes you'll start with a cloth that has nanosilver. It releases silver ions to kill bacteria on the fabric. The silver ions go into wastewater, and in the sewers will actually reform silver sulfide, a new crystal, new nanoparticle. So just because you find things, it doesn't mean it came from one place. So can be pretty complicated. But titanium dioxide is kind of the most common nanoparticle we find in wastewater, toothpaste, food. There's lots of different sources of this. So it goes down, this wastewater treatment plant just shows down as it goes down through. You remove about 90%. And we can almost always see any nanomaterials removed by about 90% through a wastewater treatment plant. And then the picture on the right, is really small, but we can find particles of titanium dioxide around 10 nanometers in size in the effluent. So the things that are released, if you have white paint, so white paint actually has titanium dioxide, but it's not nano, that's why it's white. If it was nano, it would be transparent paint, right? So when you get really small, light, visible light, passes through and isn't reflected by the material. So you do find a lot of things that look like titanium dioxide from paint. And that's some of the stuff that's removed. But it's really the smallest stuff that can get through a wastewater treatment plant. So they are inert effluents. We can find them in rivers and different things. And just going, this is in Arizona, but we can go to a lot of different wastewater plants, and we almost always find 90 to 95% removal of titanium dioxide nanoparticles. So if it's being removed, where does it go? Right, it's going to end up in the sewage sludges or the biosolids, and we'll look at that in a moment. But going through a wastewater treatment plant, some of the, you can have it stick to biomass and other organics, and if it's really large, less than about 20 microns, it'll settle out in the headworks and primary settling. Otherwise, a lot of it's going to interact with the bacteria, and that's the main mechanism by which nanoparticles are removed. They don't settle out of water, right? They have almost no density. They won't settle out. They'll only stick to things that then settle out. And the question is, we actually have done quite a bit of work with the EPA trying to understand when they go to a company, can they predict the amount of nanoparticles that would be removed during wastewater treatment? So EPA has this OPPTS kind of method, and it works really well for chemicals. So EE2, synthetic estrogen, methylene blue is a dye, silver nitrate is actually silver ion. So you can do this test and predict the amount of removal of a chemical through a wastewater treatment plant. And then the EPA puts this into different models to understand whether it would be a concern coming out of the wastewater plant. And here there's two types of biomass. It's using fresh biomass that we collect from a wastewater treatment plant and freeze-dried. So these are actually pretty good. They kind of show it's about the same. And so the EPA has been using this since the late 70s, this method to kind of pre-screen the fate of chemicals. And so the question was, does it work for nanoparticles? And this graph shows the difference between the yellow and these shaded bars is fresh biomass versus this freeze-dried biomass. And the freeze-dried biomass is what the EPA has in their protocol. So unlike the previous one where they were similar heights, here they're very different. And that is the freeze-dried biomass predicts almost no removal of the nanoparticles. The fresh biomass predicts some removal. And so the question is that the existing methods, and the industry didn't like this method with the freeze-dried biomass because it showed that nanomaterials wouldn't be removed at a wastewater plant. But clearly our full-scale sampling showed that it would. And when you use the fresh biomass, it shows these nanoparticles will be removed. So why does like this fresh biomass, what's going on with it to remove nanoparticles? Any ideas? Bugs, yeah, so it's the bugs in there, but what are the bugs doing? So it turns out that, like titanium dioxide doesn't dissolve and they won't eat it, but what it does is it sticks to their fat, right? So, it turns out bacteria have these liposomes, these fatty, things. And so nanomaterials, they always say oil and water don't mix, right? But they, chemical engineers will add to that, oil and water don't mix unless you have nanoparticles. And so it turns out that nanoparticles like interfaces, that they move to this interface between oil and water, and that's actually how you stabilize salad dressing. So you find nanoparticles in salad dressings, for example. And so it's that interface between the oil and water. And so for bacteria, it's the interface between water and the fatty, they're called liposomes, liposomes within the cell wall structure. So nanomaterials like to move to interfaces. It can be, air, water. So we found these in bubbles, that come out of aeration basins, but they really like that interface between oil and water. So they move there and they really minimize their energy. So that's the difference. When you take this biomass and you freeze dry, essentially you're denaturing these proteins. You're breaking up the fats. And by changing that structure of the fat, it really leads to this kind of misconception of what would happen. So fortunately, nanomaterials are really well removed in a wastewater treatment plant because of this interaction with the fats. And we heard a lot yesterday about oil and grease, and so I'd be really curious to get some of this fog now and see if there's nanoparticles stuck in the fog, coming from these restaurants. But then clearly, the bacteria themselves have a lot of fat. That's kind of a little picture. So we've done lots of things at full-scale plants. We've also done things kind of in the lab. And this was a fun series of experiments. We actually had a student operate, small lab reactors for a year. And twice a day, we added new, simulated sewage that had nanoparticles in them. So the black line here is just the suspended solids, the biomass growing in the plant. And then the red line was something called C60. So it's a fullerene. If you ever gone to Disney World and they have the Epcot Center, that's a giant fullerene, right? So these are nanofullerenes, right? So people use these in cosmetics and different things. So we added it at the red bar line, one concentration. We decreased it, kept it low, and then increased it again. And then we could measure the C60 coming out after the treatment. So a lot of times it's lower, it's greater than 90%. We're going to have some of these spikes. You see this, the red spike there really occurs when the biomass concentration, tanked. Something happened to that biomass, and we'll see what happened in a minute. And then as you increase the biomass at the end, we got better removal again. So a clear kind of dependence upon the amount of biomass. So what killed the biomass in there was nanosilver. So we continue to add fullerenes, and you can see the green line on day 150 when we started adding about 2 milligrams per liter of nanosilver, and we kept it operating, kept adding it every day for about a month. You see for a very short amount of time, the biomass concentration, the black line went almost to zero. So we killed almost all the bacteria in there by adding the nanosilver. But we kept going, we kept adding nanosilver, and about 3 or 4 days, bacteria grew again, and even though they were seeing the nanosilver, but the bacteria changed. Who was there kind of changed. changed from being, organisms that could degrade not just organics that we were feeding them, but also, nitrifiers in there. So it could grow again. Once the biomass grew again, we could remove the fullerenes. We could also track the removal of the nanosilver. So again, anytime you have biomass growing, we could reduce the nanosilver. So this amount of biomass, 0.5, it should actually be 0.5 grams per liter in the black line, is really low. Most wastewater treatment plants will be up around 2, but when we operated at 2 grams per liter, you removed everything and we couldn't measure it, so that's why we operated it lower. But clearly, if you have pulses or certain types of nanomaterials, it can affect, wastewater treatment. So what you want to do is to prevent pulses of anything that can kill bacteria in the wastewater. So this would be kind of a role of kind of controlling the release of nanoparticles into the source system. I won't go through all these, but nanoparticles really act very similar to if silver ions affect wastewater, silver nanoparticles will affect wastewater. It's really just nanoparticles of silver and zinc are just like silver ion delivery mechanisms. It's like driving a bus full of silver ions, and then they'll open the door and the silver ions come out. So it turns out that silver ions are really the thing that affects the bacteria, not the nano form of it. It's just a delivery device. And things like titanium dioxide don't have any detrimental impact on nitrification. So just because it's nano doesn't mean it's bad. It's what it's made out of that affects it. So whether it's, if you have a nano cadmium coming down, there's these things called cadmium quantum dots that are in LEDs and some of the TVs and different things. So industrial recycling plants and other things. For the most part, if you measure the total metal, if you measure it right, it's going to take care of whether it's a nanoform or not. So the metal itself is what's the damage, not the nanoform of it. And now we can combine different things. We can combine those batch screening experiments with models and predict the wastewater treatment plant performance. So a lot of this was funded by the EPA and understanding how to prepare industry and wastewater plants for the increased use of nanoparticles. So finally, what happens, to nanoparticles? We said, greater than 90% of it will go into the biosolids, for example. So we can go out, and there are techniques to measure nanomaterials. A host of them, seeing is always believing. So getting these images are, really difficult. It's really easy if someone says, here's the nanoparticle, they give me sludge instead, and that's a lot more work. But you can definitely find it. To do this transmission electron microscopy on a sample is, we charge about $1,000 a sample, right? So it's not easy. There are other, techniques out there that you can use in different types of water matrices. So things like C60, these fullerols, you can actually measure by things like gas chromatography or really, liquid chromatography, mass spectroscopy. That is, they behave like molecules. So you can analyze them. There's techniques to analyze carbon nanotubes, the things that are in things like paints. But the detection limits are, on the order of parts per billion, parts per million in terms of concentrations. So we spent a lot of time, developing new analytical techniques. So does anyone analyze metals? Right, and so a common way to analyze metals might be graphite furnace, or ICP, inductively coupled mass spectroscopy. So normally what you do is you digest those metals and you run it through, this ICP.
Can I swap out mics?
Sure.
I'm having a hard time with batteries.
Thanks. Batteries have nanoparticles too. What happens if you have a metal in water, you have lots of ions equally distributed in the water. But this one here shows little nanoparticles, little packets of ions. And so that when they go into the detector, they cause a pulse. And so this difference between kind of ions distributed water and ions kind of that come in a big pulse is a way we can just differentiate whether it's ionic silver or zinc or nanoforms of things. So then you count these peaks and do different things with them. straight line is not a dead nanoparticle, but what it would look like if it was ion instead of a nanoparticle. So we can do this, and this just shows a distribution of titanium dioxide sizes that we find in a river, and this is a river in Arizona called the Verde River. And this just goes to the fact that there are naturally occurring forms of some of these nanoparticles. The x-axis here is size, the diameter of these things. And you don't end up with just one. It's really a distribution of sizes. It's kind of like thinking about air pollution. You have PM10, PM2.5, and ultrafines. It's also, you have a size of these different nanomaterials. And then you see tap water. So it's actually the Verde River that went through a drinking water plant. And you can see that you remove nanoparticles and you can change the size. So drinking water plants remove over 99% of these. And then you see the wastewater has nanoparticles again compared to the drinking water. And that's because we've added in these nanomaterials. So we can measure these things. There's techniques out there. But not every nanomaterial has a technique. So I thought this would be a good example for this group. It's this company that makes a paint product where they mix in multi-wall carbon nanotubes. That's that acronym. And those come in 55-gallon drums. And then they mix it into a paint product. And so the EPA wouldn't provide, approval for this thing because the river nearby, they were afraid that you could get multi-wall carbon nanotubes in there that could affect fish. So there's been lots of studies to show the effect of multi-wall carbon nanotubes on fish, maybe 100. They picked the one that was the worst. And they said that the effluent limit from the wastewater treatment plant could not exceed 50 parts per billion. But there's no analytical techniques to measure 50 parts per billion. And so for about 3 years, this company, a lawyer, the state regulator, and the federal EPA were going around and around and around. So they asked us for some help to understand, is there a real effect, or could they give them a permit to operate? So the first thing they did was to come up with a spill scenario. So what if they spilled one 55-gallon drum that contained 5 weight percent carbon nanotubes over a 24-hour period? What would be the concentration in the sewer, and what would be removed? So it turned out, and the EPA kind of made it this way, is that the concentration in the sewer would be 100 parts per billion, which was 2 times higher than the effluent discharge limit they were regulating. And so the question is, they needed proof to show that it would be removed during the wastewater treatment plant. So we did these same types of tests, in the red bars on the right, to show that at different solids concentrations in a wastewater treatment plant, could we remove these multi-wall carbon nanotubes? And we showed that in normal conditions of 2, 3, and 5 grams per liter of biomass, we'd be way down below that 50 part per billion limit that would get discharged. But to get there, we had to develop a whole new series of analytical methods for this. And so in this case, we actually used yttrium. So yttrium, carbon nanoparticles are carbon. They're not made of yttrium. But does anyone know how you make a carbon nanotube? There's really cool YouTube videos on it. So you grow them. It's like growing a tree forest. So you start with a metal plate of iron usually, or iron and nickel, and you pass a gas over, like butane or some other gas, and you grow these carbon nanotubes. So it turns out that yttrium is a trace impurity in the iron. So we can actually use it as an isotope of yttrium that we can track. And so we could track this at very low concentrations and prove it was associated with the nanoparticle. It turns out that there's very low background concentrations of yttrium in wastewater. So in this case, when we had this very specific company with a specific product, we could do very specific analytical techniques. And now they're actually being asked to track this at the wastewater treatment plant for about a year to see if they've had any spills coming out of their facility. I'm going to skip them. So in the end, I think one of the questions is, should you be concerned about nanomaterials in wastewater? My answer is kind of no, for 2 reasons. And one is that the exposure of these things are low. So even things like titanium dioxide. It's less than 1 milligram per liter coming into a wastewater plant, microgram per liter coming out. And not only do we use it every day ourselves, but fish only respond to it at things like hundreds of milligrams per liter. So both the exposure is low and the hazard is low. Therefore, the risk of a lot of these things are low. Now, it doesn't mean we shouldn't be thinking about them, but it's not that there's a kind of impending doom out there, like some of the pharmaceuticals, which we know can have effect on fish in the ecosystem. So there's been about 15 or 20 years of work thinking about both the hazard side and then a growing body on this exposure side of being able to measure these. So if it's not in the water, where is it? And it goes to the wastewater. Anyone from Austin, Texas? All right, so I don't know if you know about this facility, this nice test study area where they apply biosolids. So we're able to work with the USDA and go out there and collect core samples and understand, where have the nanomaterials gone. So we could go out there and we could analyze lots of different nanomaterials. So we can find nanoparticles. Here's titanium dioxide, and on the left from toothpaste, and on the right from paint. But this is from biosolids. We find other particles of titanium dioxide from natural sources like dust. Touch it. Here we go. And here's titanium dioxide that's in your toothpaste on the left, and we can find the same type of thing in the biosolids on the right. So they're definitely kind of there. So we can go out into the fields and we can find titanium dioxide, at different depths in the field, which makes sense. They're not biodegraded. And if we look kind of with depth, in there, we can see that the titanium dioxide kind of stays about the same. And compared to the control site where there are no biosolids, the concentrations are higher in all the gray bars there where they've applied biosolids. So this isn't just kind of background titanium. It's attributed to applying the biosolids. So it's a pretty clear signal for titanium. We use a lot of this stuff. The story is less conclusive for things like silver, zinc, and cerium. These are other nanoparticles. Cerium, there's computer chip manufacturers in the Austin area. Cerium dioxide is one of the polishing agents, but there's really no trend that the biosolid amended sites have higher concentrations. But you can see for silver, even at the control site, there's silver near the surface. This is probably from atmospheric deposition, but clearly where you apply the biosolids, there's more silver than the non-biosolid amended site, and it stays all up near the surface. We could never find a silver nanoparticle, so it's most likely ionic silver there. So to start wrapping it up then, clearly nanomaterials are used in society, toothpaste, chicken salt, manufacturing processes, and it gets mixed with lots of different kind of, nanoparticles from the environment. So finding them can be a challenge. So this is a fun graphic I like. We'll eat several milligrams per day of nanoparticles. We apply sunscreen. We have nanoparticles in our textiles. It goes into the store where it's mixed with industrial waste. You remove about 90% at a wastewater plant. So we'll have part per billion concentrations in rivers, but then we go swimming again, we release some more. Drinking water plants will remove about 99%. So, in terms of a risk of getting nanomaterials in our drinking water, it's pretty low. In fact, it's a much higher risk that we drink, iron, copper, lead, unfortunately, that all occur in nanoforms due to the corrosion of our pipes. So the engineered part of this is pretty low. It's really the natural and incidental nanoparticles, which are much higher load into the environment than the engineered side of things. So with that, just kind of wrap it up here in terms of summarizing that graph. So they don't magically disappear. Most nanoparticles go somewhere. So with that, if there's any questions, I'd be happy to try to answer them. Thank you.
We have time for a couple of questions.
Come on, who brushed their teeth and always wondered where that went?
Who drew the stick figure?
Okay, so, I have a PhD student, and he had a really fancy one. I drew that one myself, and I'm not a very good artist, but you know what it is, right? It's, someone, it's a person, right? And that's, the only important thing. So I'm not a very good artist, yes.
So I have a question about the biosolids measuring the nano size versions of the different metals. So if you're testing for a particular metal in that biosolid, are you going to catch the nanoparticles or not?
Yeah, excellent question, right? So if you measure, say, silver, right? So the way that you would take a biosolid sample and send it off to the lab, they're going to digest it. They will measure total silver in there. That captures the nano, right? So one way to think about it is whatever metal concentration you have is like the worst case. If all of it, if it was all nano, you would capture it, right? And so it turns out that from an ecological point of view, that the hazard, or if I put in an experiment with Daphne or something with ionic silver and nanosilver, the ionic silver is always worse, right? So one is your measurement, even if your total silver was all nano, right? You capture it, and it's actually lower risk than if it wasn't nano. So what I'm saying is that what you're doing now is already conservative and would account for the nano form of it. So I think for the most part, the things that aren't being captured are things like silica, right? So you don't measure silica in biosolids. So if someone were to come along and say certain types of silica was a concern, or cerium, dioxide usually you don't measure. So most biosolids you measure, copper, zinc, cadmium, right? So it's some of these other nanomaterials which aren't toxic, like titanium, that you don't measure, that people are worried about, or ask these types of questions.
Okay, and if I can ask a follow-up, does the nano, let's say it's a metal, does the nano metal behave differently than the other metal in terms of runoff? Let's say it was spread on a field. Is there a different, is one more or less than the other more likely to end up in, say, that stream that's on the edge of the field?
Right, and so the nanoform would be more likely to end up in the stream, right? Because the ionic silver, will bind to the soil, right? More, that would be transported less. And so people have looked at, especially in biosolids, if you start flushing them with rainwater, right, which comes out. And it's actually, the nanoparticles, one reason that they stick to soil is kind of through salts and electrostatic interaction. So if you change the chemistry, you can release them. So my guess would be, more of the nanoforms would come out. But that being said, a lot of the soils actually have natural nanoparticles that silver would attach to. So, I would think that, given the question, if I had to flip a coin, I'd say it'd be more likely that the nanoforms would end up in the river than the ionic forms.
And is anyone studying that?
No, so the EPA has pretty much stopped funding research on the adverse risks of nanomaterials. Instead, our center and others now moving towards the applications. So, there are questions like that. We're studied in some large centers around the country, but they pretty much stopped. Even in Europe, they pretty much moved towards regulation. They really thought that the risks have been pretty low. And so the question is, what happens when titanium dioxide gets in a river, right? So we've looked at that. And so what happens is it interacts with sunlight and it cycles around and it produces, oxidants that can degrade pollutants in rivers, but that means it can make organic nitrogen more bioavailable. So there are lots of things that people don't know still, but the funding agencies have kind of moved away from the risks to look at the applications of nano. So let them know that they should be looking at it. They won't listen. Great.
One more.
Okay.
So do nanoparticles interact with microbial biomass in soil the way that they do in water in the GeoTechnologies?
Yeah, right. So nanomaterials will always like to move to that interface. And so people have looked at, if you've applied biosolid, people have looked at uptake into plants, as well as changes in soil microbial ecology as you've applied different loads of biosolids onto them. So there's a group at University of Kentucky that actually made biosolids and applied them to different types of systems. So, they've looked at earthworms, for example, within the soil. So, whether it's earthworms in soil or things like Daphnia, in rivers that process lots of solids. So most of the nanomaterials move through, and a very small fraction of them can move into the organism and accumulate in the organism. So filter feeders, clams and different things, also process lots of nanoparticles, and people have seen a small fraction move into the tissue, if that's your question. Well, great. Oh,
We do one more?
One more.
Yeah.
okay.
Of course.
Something back to your yogurt?
No, well, you made me worry about it a little bit, but it tasted really good, so it's okay. So with the nanomaterials going to that fatty layer around the bacteria, will they just accumulate there? Will that harm the bacteria over time?
So, one is the concentrations are low, even,
Okay.
there. And, in a way, that's kind of how bacteria will bring in iron and other nutrients is they get these natural nanoparticles of the things that they need, and then they have enzymes that degrade them and bring the ions, in. So, yeah, but, in a wastewater treatment plant, the bacteria only live, 10 or 20 days. So there's lots of things that'll stress them out. And what we found in kind of our tests is, for the most part, things like titanium dioxide won't stress the organisms, but if it is a nanosilver, right, it's kind of a packet. You are delivering a lot of ions of silver to an individual cell. So yeah, you will kill that one bacteria, but that'll actually have a less of an effect than ionic silver coming into the affecting all the bacteria. Does that make sense? So it's a little bit more site specific.
Okay.
Great. Thank you.
Thank you.
We should have warned you about the touchy clicker.
Yeah, is the ball on the podium?
There's no